So I'm Rahul Jadhav, co-founder of Accuknox. What I'm going to talk about is runtime security. And I know security by itself is hard. Runtime security is extremely difficult, comatose. I've seen people just running away from runtime security. Who am I? I became a CNCF ambassador just like a month before. Proud moment for me. I'm a co-founder of Accuknox, where we are trying to solve the problem of runtime security, how to make runtime security accessible. But that's a fancy title. What am I doing? Basically, behind the scenes, I'm a developer. So, being a Linux kernel developer for past 20 years, been working on several open sources, including Cilium. There's an open source that we started, CubeArmor. It's a CNCF project since past roughly 2 years. And I'm going to shed some more light on that particular project. What is it? What was the vision? Why did we started working on that particular project? That is the core thing that I would like to discuss here. But yeah, apart from that, I love going, visiting, and talking in the standardizations forum. Low power mesh network is my special area of interest, and I'm active in a role and LWIG and several other IETF working groups. I'm going to focus on cloud native technologies. Of course, that goes without saying. This is a cloud native tech conference. But it has found its roots in several other technologies as well. For example, you talk of edge, you talk of 5G control plane. Kubernetes is the orchestration engine of choice in all of these places. So if you're not on Kubernetes, you have a problem. And I heard one of the panelists saying about Kubernetes has a very steep learning curve. I had an experience to be quoted there in the context like, today, if we onboard a new developer, all we have to give him or her is an access to our dev cluster, and the developer figures out where all the things are. There's a standard place where all the configurations could be found. There's a standard place where all the resources could be found. There's a standard place where you can find out where the load balancer is operating. I would say that it's actually reducing the amount of time that one needs to get onboarded onto Kubernetes. So with that in mind, I'm going to keep focused on Kubernetes security. But then let me just explain what is the security angle that I'm talking about and why runtime security. In most cases, most of the organizations already have some sort of pipeline to deal with security in terms of like static scanning. Like you've already integrated with static scan code scanning tools. You have a way to identify vulnerability management, vulnerabilities in your container images. But the noise there is extremely high. And that noise is high because it doesn't really have a visibility as to what's actually happening in the runtime. What is it that has to be prioritized? And that's where the runtime engines come into play. That's what we are focused upon. So the admission time is what folks from KubeArmor talked about, right? Before your workloads are actually getting deployed, there's a check made using the admission controllers as to whether this pod should be allowed, whether this workload should be allowed to be deployed in the Kubernetes environment. That's another check. This is a new dimension that Kubernetes has added. And then once the workloads are actually deployed in the target environment, how do you secure there? Most of the attacks are manifested in the runtime, right? If the data exfiltration has to happen, it's going to happen in the runtime. If a ransomware attacker is going to start a mining rig on your Kubernetes cluster, it's going to happen in the runtime. How do you identify those aspects? So that's where I'm going to focus here. Now, runtime security by itself is not just a single dimension, right? You have network policies. Folks here have talked about Cilium and several other CNIs, which provides network security, network policies. Then there is service mesh security. How do you enable MTLS at the layer 7? How do you enable MTLS? How do you enable inter-microservices communications only for certain APIs and all of those things? Then there's systems security. And this is a relatively, what I would say, unexplored territory, where you have got to harden your workloads. What do we mean by hardening the workloads is that in the context of Kubernetes, your pod is an execution unit. Within the pod, almost everything has equal access to all the assets. Take, for example, you have a volume mount point. Within the pod, there are multiple containers. Those multiple containers have multiple binaries. All of them have equal access to that volume assets, volume mount points. Similarly, all of the binaries have equal access to the network. If the egress rule is enabled, anyone from that particular pod can talk to the egress. And that's a problem, right? I mean, typically what we have seen is that only 1 or 2 binaries need access to the network primitives. Why should it be enabled for everything? one or two binaries need access to the service account token. Why should everything be enabled? That's the problem essentially we are trying to solve with workload hardening. Identity is key, but the goodness of Kubernetes is that it provides you out of the box. You have a way to identify the workloads using a set of labels, namespace, and several other abstractions that Kubernetes provides. So that is already solved for you, but if you have a hybrid environment, and that is true for most of our users and our customers, where they have some sort of workloads in legacy environment, and how to deal with that is a pretty big challenge. If you're going down that route of synthesizing an environment where you have hybrid workloads, it's going to be a challenge. Identity is going to be one of your challenge. We are a 100% Kubernetes organization right from day one. Like our SaaS environment is built on top of Kubernetes. We were on GK, we moved to EKS. All of this migrations were simple just because of that abstraction model. It's much easier to move from one place to another, if at all needed, if you have that kind of abstraction in place. Oh, runtime security is difficult. I talked about that, right? The primary headache there is, if you're going to analyze things in your stage environment and say that this is what my runtime environment looks like, and then go deploy it in the production environment, I don't have to tell anyone here that none of the environment, none of the production environment is, none of the stage environment is same as production environment. That's the foundational problem. Like, how do you deal with that? And that's, stage environment can replicate maybe 80% in the best case, 90, but 20% is still left unexplored. How do you deal with that particular problem? You figure out a way to secure at runtime, but then your application developers are busy changing the application code, which means that your runtime security posture is no more valid. How do you deal with that problem? Application updates are going to change your security posture. How do you deal with that at runtime? That's another big problem. Attesting workload identity. In the case of Kubernetes, you have a set of primitives to do that, but in non-Kubernetes environments, it's extremely difficult. How do you know that an identity has to be assigned to a particular workload? Really difficult problem. Performance impact. Now, any runtime engine has some sort of performance impact. I mean, vendors can say that there is none, but there is always a performance impact. Why? Because you're checking things at runtime, right? You apply a network policy, which means you are inserting either IP table rules or eBPF bytecode somewhere, which implies that the packet is going to traverse through those rules, which means there's a performance impact. So that is another big challenge. Anything that you evaluate, you have to make sure that that particular angle is understood. Impact of false positives. If something is not correct, you have to take a remediation action or remedial action. That could be in the form of maybe deleting the pod or killing the process or quarantining the node. And that has a big impact on the overall application posture because your application can face downtimes. So that's another challenge. That is what we have seen. And the last but not the least, heterogeneous system. Like your runtime primitives are tied to the underlying platform. Like for example, in the case of eBPF, eBPF is still tied to Linux. There are attempts to get it on Windows as well, but still it's a multi-year project. I don't see it happening in another 5 years. But so you have to deal with multiple heterogeneous environment, and even eBPF, right? eBPF has multiple flags. It's not easy to ensure that you have an environment, you have a runtime security posture that has the right, your distributions, your systems need to have the right set of configuration. So that's another challenge. That is what I've seen. Choosing a right platform, that's again an important point. Like all the challenges that I've mentioned before, that eventually leads into choosing the right platform, right? What are the dimensions that have to be covered by the platform? Ideally, you want to cover as many as possible. The deployment mode is yet another challenge and a problem as well, because for runtime security, you need to understand what the workload is doing. We are talking about observability and eBPF and IP tables and lot of things, but they depend upon certain primitives which have to be deployed in the target Kubernetes environment. So that are deployed either as a sidecar model or a daemon set model. In some cases, it requires tweaking the host environment itself, which is difficult in hardened operating systems such as Bottle Rocket or container optimized OS. So you have to take into consideration all those deployment aspects as well. So that's another problem. Identity as a perimeter, like I said before, you need to have an abstraction for identity. Your workloads are going to be moving. They're going to be ephemeral. If you end up making use of the constructs such as IP address and host names for authorization, you will have a DevSecOps teams which is always going to be on the hook. You'll never achieve stability. So that's another point to be considered. Security approach, inline remediation versus post-attack remediation. I would shed some more light on that particular aspect in the coming slides. Probability of and impact of false positives. Does a particular runtime security engine handles, what is the impact of false positive, right? If there is a false positive and it results in something to be taken down, what is the impact of it? Performance and control over it, it goes without saying, it's self-explanatory. Now, we have been focusing on pod, container, and system hardening. The reason why we have been focusing on that, I already mentioned, in the context of Kubernetes, your pod is an execution unit. But, there's one more important thing that you have to keep in mind, that today, attacker has direct access to the pod. Attacker is directly establishing a connection onto the pod. Most of the managed cloud providers, they will provide you security solution that targets the worker nodes, and then call it shared responsibility model, saying that you are the ones who have to secure our applications. So it's your responsibility as a user, customer, that you have to secure your own applications. Your managed cloud provider is not going to do anything about it. So that's a bigger problem. This need was identified by NIST. Last year, NIST published a Kubernetes hardening guide, which included these aspects as well. Well, let us look at an anatomy of an attack. Like this is an attack called as Hildegard attack. What it did was it made use of a misconfiguration in the kubelet itself, used that for initial access. Once the attacker was inside the system, the attacker tried to use the service account tokens and then tried to do lateral movements to as many nodes as possible. Once they reached the node, they injected a new binary called XMRig, which is essentially a cryptojacking process. And then the process, those processes established a CNC or command and control connections back to the attacker's home. It used all the techniques to disguise themselves. The binary was actually injected into the Linux system as an existing process, bioset. So you won't be able to see, you won't be able to differentiate, right? You won't be able to see. It's an existing process. And then at runtime, it was able to hide using LD preload technique. So even if you do a PS, you won't see any new process in the memory. So these are the kind of sophisticated attacks that you're dealing with. This is where most of the runtime security these are the needs of runtime security. This is a chart. I know it's not readable. The intention here is that on the upper side of the diagram or the slide, what you have are a set of network controls from MITRE TTPs. MITRE is a framework which explains how the attacker, what is that the attacker will use, what are the techniques that the attacker will use, and you can then create defenses around that. In the top first half, what you have is all the attacks or techniques based on network alone, and in the lower half, you see attacks techniques based on Linux, and you see it far more surpasses the network-related controls. The point that I'm trying to make is, lot of attention has gone into network policies, and that's where the attacker is going to come in. But today we have other types of attacks where using supply chain attacks, your attacker is already going to be into your system. How do you deal with those? So you have to take into consideration all those threat surfaces as well. Introducing CubeArmor. CubeArmor is a project that we started like year and a half, 2 years before. We were dealing with the problem as to, there are basic mitigation rules in the context of MITRE TTPs. Like, a very simple rule. You have a root certificate folders. No one should be allowed to edit or insert a new root certificate folders, because allowing that would enable access to the traffic application traffic to that particular attacker. Very simple mitigation rules, but there was no policy engine which could do that, wherein it could disallow anyone to write into that particular folder. Very simple mitigation. That became the basis for our work. What we wanted to do is have a policy engine which can not only observe that someone is writing into the root certificate folder, but if some unknown process is trying to write, or even some known process is trying to write into that root certificate folder, that will be disallowed or permission denied. Inline mitigation. That's where inline mitigation comes into play. You'll see two components here. eBPF has been talked a lot about in today's different sessions. Very important tool. Importantly, it gives you observability and monitoring from the system's perspective. But you'll see a component called as BPF LSM that was upstreamed in Linux kernel roughly 1.5 to 2 years before, and it's changing the whole dynamics of systems hardening. What you can do is now you can insert BPF bytecode at LSM hooks and get inline remediation. It's very important. You might have heard of SC-Linux and AppArmor. Traditionally, these are 20 years old technologies being used in Department of Defense in US. Most of the NSA good practices are based on those hardening techniques, but they are not easy to use in the context of Kubernetes environment. So that's what we are trying to simplify here. Post-attack exploit mitigation is flawed. If you are doing post-attack mitigation, in the sense that you observe an event, you send that event to the user space, and in the user space you make a decision that you have to go and, it's a malicious event or malicious action, then you have to take a remedial action then. If you're doing this, you are allowing the attacker to actually execute the target code in the target environment. Attackers are much more savvy, and they exactly know how to hide themselves. I've shown you one of the techniques that they've been making use of. So the remedial actions such as deleting the process, killing the process, deleting the pod, quarantining the node is not going to be helpful. By the time you go and delete the pod, your sensitive assets might have been already encrypted or deleted worse. So don't do that. So there are multiple approaches. The reason why we ended up using LSMs, and LSMs is extremely difficult to use. It was a very tough decision for us to focus on that particular approach, because whoever we talked to gave us an advice. SC-Linux, please don't go there. In fact, there is a website called as turnoffsclinux.com. It has that kind of bad name. It's extremely difficult. But the point is, those are the primitives that can actually secure you. What the problem statement that we saw is that you have a solution which is unusable. Can we hide all the complexities of these LSMs under the hood and provide users, and especially Kubernetes users, a simplicity of YAML policy? That's what our aim was here. So what does inline mitigation versus post-attack mitigation looks like? That's the post-attack mitigation. In the case of inline mitigation, what we do is we observe the behavior of the application. We say, oh, these are the set of processes that needs execution within this particular pod. Those are the process set that goes into saying that only allow this process set to be executed. If there's any other process that gets executed, it's denied. If there is a process unknown process trying to access a sensitive asset, it would be denied. Unknown process trying to do a network communication, that would be denied. It's very simple if you think from that perspective, right? So our intention was simplifying LSMs. Linux security modules, very powerful technology, been there for 20 years, used by defense technologies, but not really the benefits of it were not really ripped by the general scenarios, the enterprise scenarios. So that's what our intention was. So you see how the policy looks like, a simple YAML policy, and I have some examples in the later slides. That gets converted into either AppArmor policy, SC-Linux policy, or in the case of BPF LSM, dynamically the eBPF bytecode is generated at runtime. You can do application hardening, which means that there are hardening rules from MITRE. I mentioned about that already. You have NIST 853, you have STIGs, DISA STIGs, you have CIS, you have PCI DSS. It's so many guidelines out there saying that do not allow these kind of behaviors. But there's no engine out there who can implement that kind of basic mitigation rules. That's what our intention is. Network segmentation came as a surprise to us. The basic premise of KubeArmor was that it has visibility into all the system calls. It has visibility into connect, accept, socket, raw socket system calls. Is it possible for us to actually identify which microservices are communicating to which other microservices and leverage the identity abstraction provided by Kubernetes? With that, what we did was, using the system call information, we could auto-discover the Kubernetes network policies. So there you go. You use this open source, you run it you execute your workloads, you call a command to discover the network policies, and it will give you a set of network policies in the context of your environment. Very powerful, very easy to execute. Set of sample demo policies. Here you'll see, do not allow anyone to access service account token. A lot of times, in the case of Kubernetes, service account token is mounted by default in the pod. There is a configuration where it can be disabled. But it's an explicit configuration that the user has to set, and in most cases, it goes unnoticed. So in most cases, your service account token is going to be by default mounted in your power. A very simple policy, just a 2-line, actually a 4-line policy. Important thing is action is block. So it's not like if someone accesses service account token, someone else is notified, and then someone else will go and kill that process. That flow is not going to work. By the time that flow works, the attacker might have already done the job. What our intention is to block in the first place. Like if some process tries to access service account token, do not allow it. So recap on the Hildegard attack, right? What is the KubeArmor protection that can be provided here? In the context of malware, as I forgot to mention, KubeArmor is a CNCF Sandbox project. I think I mentioned. It's a year and a half, 2 years, been into CNCF. We went to CNCF primarily because we ourselves were not sure of the approach. When we got to CNCF, we got immense guidance from that team, saying that someone from Kubernetes 6 security group had already tried the one particular approach that didn't work, so you better don't do that. You do it this. So that's the kind of guidance that we've received from Kubernetes groups. Very happy about receiving that kind of guidance. But the point is, for every attack point in the context of Hildegard, you have service accounts. Service account access can be strictly controlled, saying only this process should be allowed access to the service account token. Similarly, in the case of launching cryptojacking operations, there's a binary XMReg which is getting injected within the pod. Any unknown binary, any new binary won't be allowed to be injected. If it tries to be, even if the injection is successful, it's a defense in depth, right? You have to have defense at multiple levels. Even if the injection is successful, your execution won't be allowed, like execution of that binary won't be allowed because it's an unknown process, and things like that. CNC connections, you have an unknown process now trying to attempt network connections. Do not allow that, very simple rule. Use of Linux process name, you are now changing the system's binary folder. By default, it is assumed that no one changes anything into the system's binary folder, so that's already locked down. So no one is allowed to make changes into existing. The last part, LD preload. LD preload is a user space technique where you can modify, where you can, if it's a shared library, you can override the library call. And with that, you will be able to disguise the process. Since this is a kernel space technique, all those problems do not exist. So that's essentially the advantage. To summarize, I've talked enough. Runtime security is difficult. The primary advantage of static scanning is that it's very easy to deploy in the sense that you have CI/CD pipeline where you run your code, scan your code, scan your container image, and you get a list of issues. That is a difficult problem that we are trying to solve here. Choosing the approach, that is very difficult. It has to be technically understood what the engine is doing under the hoods. There are several approaches available out there. I've seen approach where you are required to change the glibc. I've seen an approach where you are required to change the runc and insert your the vendor inserts his own runc. These kind of approaches, if you're going to take, it's going to introduce more security gaps, security holes than solving it. Our intention was that we knew that this is going to have an impact on the security community. Intention was to keep it open source right from day one. It's completely open source. Even in our enterprise version, we do not maintain a downstream fork of KubeArmor. The whole KubeArmor is open sourced as it is. So that's what this talk is about. We are looking for more maintainers. We have already 110 contributors in KubeArmor. We are looking for open source evangelists. If you think you are the person, please contact me. Would love to connect. Thank you.